Welcome to Lecture 7, in which we will review the idea of inner product, and we'll also talk about another idea called the Bloch sphere. I want to review inner products and the bra and ket vectors because there have been a few questions about those ideas, and I want to make sure that we're all together on that. If we have a state C, and we want to measure it with a measuring basis, that consists of some ket V and V orthogonal, and this is assumed to be an orthonormal basis, as is the case with all of our measuring bases. Then we know that the way that we can express the state C in terms of that basis is as follows. We could write it as A multiplied by V plus B multiplied by V orthogonal. And then if we take the inner product of both sides with V, we will get this equation, and then from that point we reason as follows. We say that since V and V orthogonal form an orthonormal basis, then V and V orthogonal are indeed orthogonal to each other, and therefore this inner product is 0, so the second term goes away. And furthermore, since these vectors are orthonormal, then the inner product of V with itself is 1, and so the right-hand side is simply equal to A times 1, which is A. And therefore, we get A is equal to the inner product of V with C, and B is equal to the inner product of V orthogonal with C, and the probability of measuring V is A conjugate, and the probability of measuring V orthogonal is B conjugate. And my impression is that everybody understands these concepts well. The only difficulty is when we actually put this in practice, and I believe that in that case there might be a few misunderstandings, and so I wanted to look at this in a little more detail and make sure that we're all together, because this is an important idea. So let's look at an example. We're going to say that our measuring basis is the basis. This is in your book. Let's see if I can find real quickly what page. Okay, this is on page 22 of your book, and this is something we have not talked about before, but it will be the following. I and minus I. And let's explain what that means. The I cat is equal to 1 over square root of 2 times the 0 cat plus I times the 1 cat. And minus I is equal to 1 over square root of 2 times the 0 cat minus I times the 1 cat. Now, before I even proceed to express a vector in terms of these basis vectors, I want to challenge you. And the challenge is this: verify that these vectors are an orthonormal basis, or let's just say are orthonormal. And I really strongly encourage you to stop the video now and try to show that these vectors both have unit length and that their inner product with each other is 0. If you can do that, actually probably the rest of this review is even unnecessary. But I'm suspecting that some of you may have difficulty in verifying this, and so that's what we want to address with this review. So stop the video now, try to verify that these vectors both have an inner product of 1 with themselves and 0 with each other, and then when you're done, let's all come back and look at this together. Okay, so in order to verify what we want to verify, there's basically 3 things we want to verify here. Verify that the inner product of I with I is equal to 1. The inner product of minus I with minus I is equal to 1, and that the inner product of I with minus I is equal to 0. These are the 3 things that we want to verify. I'll call that maybe A, B, and C. And let's start with I. Okay, the way that I want to talk about this is the following. Okay, I is equal to, as we've already written, is equal to 1 over square root of 2, 0, plus I times 1. And remember, this is called a ket. Now, this notation is called a bra, and it is said to be the dual of the ket I. Now, the important thing to know here is the following. In general, the dual of alpha V is alpha conjugate times the bra V. So let me say that in another way. The dual of alpha times the ket V is alpha conjugate times the bra V. Okay? And now that we're armed with that information, we can say the following, that the inner product of I with itself is obtained by pre-multiplying I by the dual of I. Okay? Now let's look at this. If I, well, I won't say if, I'll say since I is equal to 1 over square root of 2, 0, plus I times 1, the dual of I is, now remember, what we're going to do to take the dual is we're going to take the complex conjugate of any scalar multiplier, and we're going to turn every ket into a bra. So we will get 1 over square root of 2 conjugate times the bra 0 plus I conjugate times the bra 1. And furthermore, this is denoted since we have this notation here. This is for the ket I, then the dual of that has this notation. So what we have just verified, or what we've just stated, is that the dual of I is equal to 1 over square root of 2 conjugate times the 0 bra plus I conjugate times the 1 bra. And once again now, just look at these two equations. What we're saying is when we take the dual of a ket, any scalar part will get conjugated, and any ket will be turned into a bra. So this ket is turned into this bra, this ket is turned into this bra, this scalar is conjugated to give this scalar is conjugated to give this. And of course, 1 over square root of 2 is real, so when we take the complex conjugate, we still get 1 over square root of 2. But for I, this is imaginary, so when we take the complex conjugate, we get minus I. So minus I, and oops, I've done it again here. So that's the dual of I. And now to get the inner product of I with itself, well, we get, when we pre-multiply, okay, we said we needed to pre-multiply I by its dual, so we have 1 over square root of 2, 0, minus I, 1. That is pre-multiplying, and by pre-multiplying I just mean it's to the left of it. That is pre-multiplying 1 over square root of 2, 0, plus I, 1. And when we now multiply everything out, we will get 1/2, 0, 0, plus I over square root of 2, 0, 1, minus I over square root of 2, 1, 0, and minus I times plus I is minus of a minus 1, so plus 1 times 1. Well, we don't want to forget. I've made a mistake here. This should be over square root of 2 as well. So this is square root of 2, and here's the square root of 2, and here is the square root of 2. And so this should be I over 2, I over 2, and then here 1/2, 1, 1. There's still another sorry, I guess I've made this mistake throughout the entire presentation. So just to make sure that this is clear, the cat I is defined as 1 over square root of 2 times the 0 cat plus I over the square root of 2 times the 1 cat. So I wrote that down incorrectly initially. Make sure that you get that. As you will see, now with that factor included, we will have all the correct results. Otherwise, we would not have had the correct result for the inner product of I with itself. So make sure you get this. Okay? And let's see. Yes, it's correct up here. It's correct here. But when I brought it down here, I forgot this square root of 2. Okay? So now that that's been taken care of, I believe that it's taken care of everywhere down here now. Let's see, we need a square root of 2 here. And yes, I believe we're all set now. Okay, and so to finish this up, of course, 0 inner product with 0 is 1, 0 inner product with 1 is 0, 1 inner product with 0 is 0, and 1 inner product with 1 is 1. Let me make this line a little clearer. So we get 1/2 times 1 plus I over 2 times 0 minus I over 2 times 0 plus 1/2 times 1 is equal to 1/2. Excuse me, equal to 1/2 plus 1/2, which is equal to 1. And that checks, that verifies the first thing that we wish to verify. And so now for B, we want to verify that the inner product of minus I with itself is also equal to 1. And I don't believe, having seen what we just saw, I don't think you'd have any problems. But just to make sure, I'll do this real quickly. So we have minus I is equal to 1 over square root of 2 times the 0 cat minus I over the square root of 2 times the 1 cat. And therefore, the dual of that will be 1 over square root of 2, 0 plus 0 plus I over the square root of 2, 1. And now when we pre-multiply the cat by its dual, we will get minus I equals 1 over square root of 2, 0 plus I over square root of 2, 1. 1 over square root of 2, 0, minus I over square root of 2, 1. And so we will get that, and that will be 1/2 of 1 minus I times 0 plus I times 0 plus 1, or 1/2 of 2, which is 1. And that verifies the second thing that we wish to verify. And now finally, we want to check the inner product of I with minus I. And we have already found that the first of these, the dual of I, which is, you can see here, is pre-multiplying minus I. The dual of I was equal to 1 over square root of 2, 0, minus I over square root of 2, 1. And minus I is 1 over square root of 2. This is the minus I cat, is 1 over square root of 2, 0, minus I over square root of 2, 1. And now let's multiply this out and see if everything checks. We will get 1/2 here, and we'll have 0, 0, minus I, 0, 1, minus I, 1, 0, and then finally minus I times minus I, minus times minus is plus, and I times I is negative 1, so minus 1, 1, and that will be 1/2 times 1 minus 0 minus 0 minus 1, and that is indeed 0. So if we think of the inner product as just a pre-multiplication of a vector by a dual vector, then I think that we will then have no problems in determining, well, we need to remember that, and we also need to remember that the dual of a scalar times a ket is the complex conjugate of the scalar times the corresponding bra. If we will remember those two things, then we should have no problems. So let's look at an example here. One final example of this before moving on to our second topic for this lecture, which is the Bloch sphere. Suppose we want to express the following vector Okay, so we want to express this vector, square root of 1/3 times the 0 ket plus I times the square root of 2/3 times the 1 ket in terms of this basis that we've just learned about, the I and minus I kets. So how would we do it? Okay, and let's just go ahead and write it like that. Okay, so what we will do is we will pre-multiply okay, well, let's I guess this is what I'll say. So in other words, we want to find A and B such that C is equal to A times the I ket plus B times the minus I ket. This is what we want to do. And we know from previous experience, since I and minus I form an orthonormal basis, we know that A is equal to the dual of I pre-multiplied by C, and B is equal to the dual of minus I pre-multiplied by C. So A is equal, okay, we know that the dual of I is equal to 1 over square root of 2 times the 0 bra minus I over square root of 2 times the 1 bra. And that's pre-multiplying C, which is square root of 1/3 0 plus I times the square root of 2/3 1. And therefore, A is equal to square root of 1/6 0 0, and then really the 0 1 and 1 0 terms we can drop out. We don't even have to worry about those because we know we get 0. And then the 1 1 term will be minus I over square root of 2 times I square root of 2/3. So we will get minus I times I is 1, so plus square root of 1/3 times 1 1. And this Since 0 is 0, the inner product of 0 with itself is 1, and the inner product of 1 with itself is 1. We get square root of 1/6 plus the square root of 1/3, and we can change this to square root of 6 over 6 plus square root of 3 over 3, which is square root of 6 over 6 plus 2 times the square root of 3 over 6. And so we get square root of 6, which is, let's say, square root of 2. That's square root of 2 times the square root of 3 plus 2 times the square root of 3 over 6. And so one way we could write A is to say that A is equal to 2 plus the square root of 2 times the square root of 3 over 6. And finding B would go in a very similar fashion. B is equal to the dual of minus I pre-multiplied by C. And so that is equal to 1 over square root of 2 times the 0 bra plus I over square root of 2 times the 1 bra. And then C is square root of 1/3, 0 cat, plus I times the square root of 2/3 times the 1 cat. And therefore B, again, I'll drop out the 0, 1, and 1, 0 terms because we know that goes away. So we get square root of 1/6 then minus square root of 1/3 and there would be B. So this is a more general case to show how we handle this conjugation when we change when we get the dual of a vector. And I hope that that will help you in future problems. So now that is the end of that topic until our problems. But let's now start a brand new topic called the Bloch sphere. And the idea here is that we wish to associate with each state vector A0 plus B1 some point on the unit sphere. Now we're talking about the sphere, again, it's the unit sphere, so this is a sphere of radius 1. So the first thing we'll note is that to pick a point on the unit sphere all we need to do is to identify the angles theta and phi. And here, in case you're a little rusty on this, I'm talking about the usual spherical coordinates. If this is the x-axis and the y-axis and the z-axis, and here is some point on the unit sphere, then we simply draw this arrow from the origin to that point, and the angle that that arrow makes with the z-axis is called theta, and when we project that arrow down into the xy plane, the angle that its projection makes with the positive x-axis is phi. And so let's see how we're going to make this association. Okay? I'll call this, let's see, I want to be consistent with the notation that's in your book here. I will just call this state as I've already written above, A times the 0 ket plus B times the 1 ket. Now, A and B, you should understand from our previous discussion that in general, A and B are complex. And therefore, we can write both of these complex numbers in polar form. In other words, our state vector could be written as the magnitude of A times e to the I phase of A times 0. And likewise, B could be written as the magnitude of B times e to the I phase of B times 1. Now, let's associate with this state vector the vector that we're going to basically map that vector to another vector. And what vector do we want to map it to? We will associate with it the vector A0. We will map it to itself, but with just one modification, and that is divided by e to the I times the phase of A. So all we're doing here is we are taking the vector that we're interested in, the state vector that we're interested in, and pre-multiplying it. You might think, or well, multiplying it doesn't matter, pre-multiply or post-multiply, because this is just a scalar, by e to the minus I times the phase of A, or dividing it by e to the positive I times the phase of A. And so let's see what we get then. If we divide this expression here by e to the I phase of A, then we will simply get A times the 0 ket plus the magnitude of B times e to the I phase of B minus phase of A times the 1 ket. Okay? And we are going to identify that with cosine of theta over 2 times 0 plus e to the I phi sine theta over 2 times 1. So in other words, the Bloch sphere representation associates the state let me rephrase this. Okay, so let's read this now. The Bloch sphere representation associates the state cosine theta over 2, 0, plus e to the I phi sine theta over 2, 1, with the original state, let's say the original state rather than an, with the original state A0 plus B1. And here theta and phi are chosen so that cosine theta over 2 is the magnitude of A, sine theta over 2 is the magnitude of B, and phi is equal to the phase of B minus the phase of A. And of course, with this theta and phi, we can choose a point on the sphere. Now, I don't want to do too many examples of this, but I do want to do just a few, and then we'll get to problems. Okay, so examples. Let's maybe take the 0 ket. When we take the Bloch sphere representation of that, what does it get associated with? Well, it gets associated with cosine theta over 2, 0, plus e to the I phi sine theta over 2, . 1, where cosine theta over 2 is equal to the magnitude of A, sine theta over 2 is equal to the magnitude of B, and phi is equal to the phase of B minus the phase of A. Now, remember, the assumption is that our original state is written as A0 plus B1. So we can see in this case A is equal to 1 and B is equal to 0, and therefore cosine of theta over 2 is equal to the magnitude of 1, which is just 1, and the sine of theta over 2 is equal to the magnitude of 0, which of course is 0. And phi is equal to the phase of 0 minus the phase of 1. And the phase of 0 is simply 0 radians. The phase of 1 is 0 radians. And so this is 0 minus 0, which is 0. And so phi equals 0 radians. And what about theta? Let's come back up here to the information for theta. The cosine of theta over 2 is equal to 1. Then the sine of theta over 2 is equal to 0. And so we have that theta is equal to 0. Theta is in the range from 0 to pi, and phi is in the range from 0 to 2 pi. So theta is 0 radians, and phi is 0 radians. And so we could say that if we're looking for the point on the Bloch sphere, we can say that 0 is associated. Now, if both theta and phi are 0, we come back up here, and of course theta equals 0 means we're along the z-axis. Phi equals 0 really doesn't enter in here, so we're at the point on the unit sphere. We're on the point 0, 0, 1. Now, let's ask, what about, this is the last example I want to do, what about 1? The 1 ket. Please stop the video and try to do this yourselves first, and then we'll look at it together. Okay, well, the 1 ket is, again, we want to write our original state as A times 0 plus B times 1. And so it's clear in this case A is 0 and B is 1. Now remember, cosine theta over 2 is equal to the magnitude of A, which in this case would be magnitude of 0, which is 0. The sine of theta over 2 is equal to the magnitude of B, which is the magnitude of 1, which is equal to 1. And from those two pieces of information, what is theta equal to? If the cosine of theta over 2 is 0 and the sine of theta over 2 is equal to 1, then theta must be equal to pi. Now, what about phi? Well, phi is the phase of B minus the phase of A. So this is the phase of 1 minus the phase of 0, which is 0 minus 0, or 0. And so we have phi is 0, and theta is pi. And so what is the point on the Bloch sphere? Well, it is the point 0, 0, negative 1. So, interestingly, the ket 0 is associated with a point on the very top of the Bloch sphere, and the ket 1 is associated with a point on the very bottom of the Bloch sphere. And of course, we know that 0 and 1 are orthogonal to each other. And in fact, it can be proven, and I very strongly encourage you to try to do this yourselves, but it can be proven that any two antipodal points on the Bloch sphere, in other words, if you take some point on the Bloch sphere and then some point that is directly opposite on it on the Bloch sphere, in other words, you connect the 2 points that are connected by a line through the very center of the Bloch sphere, any 2 points on the Bloch sphere that are connected by a line through the origin correspond to two states that are orthogonal to each other. I strongly urge you to try to prove that. So let's even write that down. Try to prove that any two antipodal points on the Bloch sphere correspond to states that are orthogonal to each other. This will give you practice with the Bloch sphere idea and also practice with the inner product. So we'll practice both of the ideas that we've been discussing in this lecture. And so now for the problems, and these will be the last problems that we will do in Chapter 2. Our next lecture will begin the discussion of Chapter 3. But let's look at some problems for this chapter. So now let's look at some problems for this lecture. In the first one, we will review what we said about inner products. And so the problem is as follows. We have a state vector psi, which is equal to alpha times the 0 ket plus beta times the 1 ket. And we have an orthonormal basis considering the kets v and v orthogonal. And we're told that v is equal to gamma times the 0 ket plus lambda times the 1 ket, and that v orthogonal is equal to minus lambda times the 0 ket plus gamma times the 1 ket. And here you're told that alpha, beta, gamma, and lambda are all complex numbers. And so if we express the state vector psi in terms of v and v orthogonal as a times v plus b times v orthogonal, find b. And you need to determine which one of these four expressions is the correct expression for b. Now the remaining two problems deal with the Bloch sphere concept. And again, even though I'm not requesting you to turn it in, I hope very much you will try to prove that two antipodal points on the Bloch sphere represent orthogonal states. But for the problems here, the questions are as follows. In 7.2, I'm asking you for the Bloch sphere angles theta and phi for the plus ket, and you have the choices pi over 2, pi, 0, pi over 2, pi over 2, 0, and pi over 2. And each pair, the understanding is that the first angle given represents theta, and the second angle given represents phi. And in problem 7.3, a similar kind of problem. What are the Bloch sphere angles for theta and phi? The Bloch sphere angles theta and phi for the ket minus I. And those are pi, pi over 2, pi over 2, 3 pi over 2, 3 pi over 2, pi over 2, and pi over 2 pi. So those last two questions should give you some practice with the Bloch sphere concept. And that wraps it up for lecture 7. And so good luck.